Today we are going to do a slight turn in our order of seminars. As I see that today's seminar would be elements of hydrodynamics, but the previous lecture was about real gases, so I think we should have a seminar about the problems related to real gases and Joule Thompson effect. So before we start, I would like to ask if any one of you remembers still Wonderwise equation. What was the Wonderwise equation? So let's assume for simplicity that we have one mole.
The pressure plus
pressure plus A divided volume
B
squared.
volume minus B
B minus
equal
R2.
Okay, that's right. So for today's we have two zero-level problems and slightly more of Irodov problems. So let's start with some zero-level problems in order to warm up. So it says, the first problem says, how many times, oops, not how many times, is the Wonderwise gas pressure higher than its critical pressure when its volume, I think it says that you want to find P over P critical if we know that V over V critical is 5 and T over T critical is 5.7. Any question there? Yeah, we have changed the order, so I have made a slight turn, and instead going to the 6th-week seminar about hydrodynamics, I went directly towards the 7th week about real gas. Okay, so probably as you see, like you have some feeling that this is somehow related to a reduced Wonderwise equation. In that equation, we had something like P plus 3 over phi squared times 3 phi minus 1. Okay, you can write phi minus 1 over 3. Okay, that doesn't matter, equals to 8 tau, where pi is P over P critical, phi is the dimensionless volume, the ratio between the volume and the critical volume, and tau is the dimensionless temperature, which is determined as temperature over the critical temperature. Okay, so actually what we have here, we need to find the value of pi if we know the value of phi and the value of tau. So it's actually a straightforward problem. I need to get this pi out of this equation, but this equation is linear with respect to pi, so I don't expect any kind of difficulties for this equation. So first I have written this equation already. So how do I determine pi from here? How do I express pi from this equation? I assume that phi and tau are something known parameters. Okay, so let's say this pi is located in this first bracket. So first of all, I need to somehow find out the value of the quantity which is inside the first bracket term in this product. So I can get this 3 phi minus 1 to the right-hand side. And after that, I need to subtract this 3 over phi squared. And so then I get my pi. So that is if I do all of that, I would get the following answer. 8 tau over 3 phi minus 1 minus 3 over phi squared. And so this is a very simple equation, and now I just need to plug in all of these values into that equation and calculate the final answer. So what I get here is 8 times 5.7, that's tau, divided over 3 times 5 minus 1 minus 3 over phi squared. That would give me 25. 25, 3 over 25. Okay, so that looks like not so good, but let's nevertheless try to calculate it without using any calculators. So in here, if I calculate the denominator, I would get 14. So this is something over 14. Okay, as I see that I have 8 in the numerator, so 8 over 14 is something like 4 over 7. So I can write that this is 4 times 5.7 over 7 minus 3 over 25. Well, actually, the most easiest way to get around with this quantity is just to use the decimal representation. 3 over 25 is 12 over 100.
0.1.
Yeah, 0.12. Okay, so now we are closer to the answer, so that I have here, if I multiply 4 by 5.7, that would give me 20 plus 2.8. So 22.8 over 7 minus 0.12. Okay, so now we are getting close. I need to calculate 22.8 over 7. So I remember my primary school and remember how to calculate these fractions. So 22 over 7 gives me 3. So that is 21. 22 minus 21 gives me 1. 1.8. 1.8 over 7 gives me something like, let's say, 2. Yeah, so, but I have something left because I have 14. So that would leave me with 4. Now I have 40 here, so in order to get around with 40, I need to have, for example, something like 5. But I think I want to stop on this second decimal point. So I see that 40 is somewhat closer to 42. So I think the approximate value would be 3.26. So now I have 3.26 minus 0.12. So that would give me 3.14, which is, well, I think this should be expected given that the quantity which we need to calculate is pi. So you see pi 3.14, so everything makes sense, so I think this answer should be expected in this problem. Okay, so any questions about this? No. But, well, just a short disclaimer, I think this is an accident, but you know, there is never an accident, but in here it's an accident, really. That pi is 3.14. Yes. Okay, so now we get to the next problem, which is the problem number 20. Oh, that's about something like entropy. Find the entropy change of an ideal gas throttled through a porous partition if the initial pressure P1 is 4 atmospheres and the final pressure P2 is 1 atmosphere. It says for the ideal gas. For the ideal gas. That's interesting, for the ideal gas. Okay, we have some initial pressure, we have final pressure, and there is some change in entropy. So again, if we have a gas throttling process, that means that H1 equals to H2, so this can be written without any kind of a thinking, but I need to somehow think how it is related to the entropy. Okay, now let's go from the side of the entropy. Entropy, according to our second lecture about second law of thermodynamics, entropy is a function of state. A function of state. So that means that if we are somehow able to calculate to calculate the initial state and final state, then we would be able to calculate the entropy. Okay, so we have ideal gas. So if I have H1 equals to H2, that means that its entropy, which is for ideal gas equal to Cp times T for 1 mole of gas. That means that T1 equals to T2. So I have some sort of isothermic process. Isothermic process, isothermic process in which, well, temperature in the initial state and the time and the final state is the same. So if I have, for example, a PV diagram, I can even plot all of these states. So in here, the P1 is here 4 atmospheres, and P2 1 atmosphere, and I have isothermic. So I have initial state here, final state here. No, it's not isothermic, it's isothermic process, and moreover, it's irreversible process, so I cannot connect these 2 points with this line, because I'm not doing any kind of a reversible isothermic expansion. I do something else. I do gas throttling. So as you know, I cannot plot a curve on the PV diagram corresponding to such process, because it's irreversible. So, but I need to calculate entropy, and entropy change can be found by considering a reversible process which connects the initial and the final point. So for calculation of the entropy change, it's a good idea to consider an isothermic process instead of this gas throttling. I consider isothermic process which connects the initial and the final point. And here I have V1, V2. And actually I know that V2 equals 4 times V1. Guess why? Why the final volume is 4 times the initial volume. Yeah, it's PV equals constant. So my pressure has decreased by a factor of 4. That means that to preserve constant PV, I need to increase the volume by the same factor of 4. So V2 equals to 4 V1. Okay, so in order to calculate the entropy change, I need to, oh, well, that's isothermic process. So I need to calculate integral of delta Q over T. Process is isothermic, so I need just to calculate Q over T. And now I apply the first law of thermodynamics. So that gives me, for example, that gives me delta U plus work done divided by temperature, but in isothermic process there is no change in the internal energy, so I need work divided by temperature. Okay, and calculation of the work in the isothermic process was the very first, I think, zero-level problem which we have considered in our course. So actually, the work done in isothermic process is something like PV times, or something like PV times logarithm V. And now, okay, V2 over V1. So here you have P1 V1, logarithm of V2 over V1 divided by temperature. Let's check it. So work done is integral of P dV. Okay, so that gives me that pressure is actually is equal to RT over V times dV. So that should be RT logarithm V final over V initial. So the products of pressure also works, but I think it's in this form it's better, because in here I need to apply this PV equals to RT, but at the end I have R times logarithm of V2 over V1. Okay, I know that this is 4, V2 over V1 is 4, so the final answer is R times logarithm 4, which should be something like, let me say, I don't know, I would expect that this is something like 1.5 times R. something like 12 joule per Kelvin mole. Let me see if okay, I have missed by 0.5 of joules per Kelvin, and okay, I have one the entropy change per mole, of course. So I need also to add to add moles to the answer. Okay, so this is a good estimation. So we get the answer, but there should be some other way to get the answer. And in here, I have got the answer by considering a reversible process which connects my point 1 to the point 2. But I could have gone some other way and just simply used the equation for the entropy of the ideal gas. For the ideal gas, entropy is equal to CV logarithm T plus R logarithm V. And I have derived this expression previously, and actually the consideration of this isothermic process is a part of the derivation. So actually it was included in this derivation. So now I can do this the same way, so that would give me delta S equal to CV logarithm of T2 over T1 plus R logarithm of V2 over V1. And as we know, in the Joule Thompson process, the temperature remains constant. That's why I have 1 under the logarithm, and the logarithm of 1 is 0, so I can eliminate this term, and again obtain the same answer as R times logarithm of V2 over V1. Okay, so I think it was quite simple. It would be nice to have it this simple in the homework, but probably there would be something more complicated than this. So we need to solve Irodov problems in order to get used to the level of complexity of Irodov problems. So the next problem is 2.203. Yeah. Two and 3. The problem says, what fraction of volume of a vessel must liquid ether occupy at room temperature? So T equals to 300 Kelvin. That's the usual value for the room temperature used in problems. In order to pass into critical state when critical temperature is reached. Ether has critical temperature of 467 kelvins and critical pressure of 35.5 atmosphere. 35.5 atmosphere, and moreover it has molar mass of 74 grams per mole. What fraction of the volume of the vessel must liquid ether occupy at room temperature in order to pass into critical state? So, well, we need to understand what actually happens as I increase temperature in this vessel. For this, I think it might be a good idea to have some PV diagrams. So let's say I have an isotherm at 300 kelvins. And I have an isotherm at the critical temperature. So I have also an isotherm at critical temperature. Okay, so this kind of an isotherm includes like some kind of a partial filling of the liquid. So in here, In here, there is no liquid in my vessel, so it's only gas. But at this point, it's filled with liquid fully. So fully filled with liquid. But what we need to have is that the volume of the vessel should be exactly equal to the critical volume. Okay, since these are isotherms for 1 mole, and we have which amount of this ether? Which function? We don't know yet the amount of the ether in this vessel, so let's assume that I have new moles in this vessel, and we don't know even the volume of the vessel, so let's assume that I have V, so V0 as the volume of the vessel. But actually, in order to pass into the critical point, these two quantities should be connected. So what I have, so if I increase the temperature but the volume remains constant, that means that my volume of the vessel should be equal to the amount of ether inside, inside the vessel multiplied by the critical volume of the ether. What we need to find actually is that we don't know yet the critical volume, but we understand that critical pressure, critical volume, and critical temperature are somehow related to each other. And if we assume, for example, that ether obeys Wonderwise equation, then we can write that, what it was there, that P critical, V critical should be equal to, I assume that it should be equal to something like 8/3 RT critical. So let's check if I am correct or not. So I need to look up the equations for critical volume, pressure, and temperature. Critical volume that I have derived during the previous lecture was 3B. Critical pressure was A/27B squared. So that means that P critical, V critical is A/9B. And at the same time, T critical, critical temperature, is given by RT critical equal to 8A/27B. 27B. So, okay, it's vice versa. So I need to have that instead of 8/3, I need to have 3/8 RT critical. So if I multiply by 3 and divide by 8, I would get exactly A/9B. Okay, so that means that I can determine the critical volume from this equation, and that would be 3/8 RT critical over P critical. And that's for 1 mole of the gas. And now let's say that I have determined, I have found the amount of ether in my vessel. So how can I calculate which part of the volume that liquid part of ether occupies? Well, in this case, I think we need to assume that far from the critical point, for example, at room temperature, the density of gas is much lower than density of liquid. And we can even calculate volume occupied by liquid in this case. So we can calculate it like follows. First, we determine the mass of ether. Mass is equal to the amount of matter multiplied by molar mass, which is given in our problem. Nu times capital M. Then that means that volume of the liquid is M over the density of liquid. This is approximately, but the accuracy of this approximation should be sufficient for our purposes. So m over the density of liquid, so that would give me nu m over rho liquid. And then in order to calculate the final answer, which is the fraction of the volume occupied by the liquid, I need to find the ratio of the volume of liquid to the volume of vessel V0. So that gives me nu m over rho L over nu V critical. And lucky we are that the initially unknown variable, which is the amount of matter, is cancelled out. So I have the molar mass over the density of liquid multiplied by the critical volume. So let's say molar mass over the density of liquid multiplied by the critical volume. Okay, so what's left over to know is that we don't know the density of ether. We don't know the density of ether, and there are two ways around this. The first way, so now we like on the splitting path, so we can go left and we can go right, and we can do this in two different ways. The first way is we can assume that ether obeys Wonderwise equation both at room temperature and at the critical temperature. So that Wonderwise equation fully describes the behavior of ether everywhere. And that means that we can actually do the following task, that we can plot this Wonderwise curve. So isotherm at 300 kelvins, and then find this pressure in the equilibrium between liquid and gas phases, and finally calculate the volume occupied in the liquid phase and in the gas phase by solving the Wonderwise equation. It would be quite a complicated path because it involves solution of the cubic equation, which is slightly difficult. So I think so this is the first path, and the second path is much simpler. We should get some kind of a reference book. So I think this should be some kind of a physical constant of the properties of ether. And in case of Irodov, the physical constants which are not supplied or which are not given in the problem can be found in the end of the book. So if you look at the end of the book, then probably you can find the density of ether. Okay, here we go. It has lots of equations, constants, properties, some for whatever problem. So the density of substances, liquids, ether. Oh, we have the on the page or in the page. How is it correct? Probably in the page. In the page 3 and 74, we have a desired density of ether, which is 0.72 of grams per cubic centimeter. Grams per cubic centimeter. So now I can calculate that the raw liquid is 0.72 grams per cubic centimeter. Okay, now I have everything. So I can just plug everything in and calculate. Okay, probably I have calculation of V critical here. I can just plug this expression for V critical in my equation. So that would give me m over raw liquid times, okay, 3RT critical. And here also I get P critical and also 8. So now I need to plug everything in. So that is 8 times 74 grams per mole. I keep the dimensions because I have not transformed everything into SI units. So I need to be careful with these dimensions. So in here I have 3 times 0.72, this is dot, 0.72 of gram per centimeter cubed times 831 joule over Kelvin over mole times T critical, which is 467 kelvins. Okay, kelvins and kelvins cancel out. Moles and moles cancel out. Grams and grams cancel out. And now I have also critical pressure, 35.5 atmosphere. So this is 35.5 times 1 atmosphere is approximately 10 to the power of 5 of pascals. Okay, so now what I have here. If I take centimeter cubes here, I would have Pascal per times centimeter cubed over some joule. So I think I need to convert these centimeter cubes into cubic meters. So I cannot go around this. I need to convert one quantity into another quantity. So, okay, so let's do it. 8 times 74 times 35.5 times 10 to the 5 times Pascal times centimeter cubed. Then in the denominator I have 3 times 0.72, okay, times 831 times 4 and 67. And in here I have also joules. So if I take Pascal and joules, what is left here is cubic meters. Okay, the question to the audience, why joule equals to Pascal times cubic meter? Okay, Pascal is Newton per meter squared times cubic meter. That gives you Newton per times meter. So Newton times meter is indeed joule. Or actually, you can remember that that actually PV equals RT. Yeah, and PV is actually, this is pressure, this is volume. This is RT. And RT has units of energy, because, okay. And nu RT, and nu has actually, yes, moles, so everything is again collected into the energy. So whatever way you want. Okay, now to calculate this, it's actually quite cumbersome to do this without the calculator. I can only do one step. This step is as follows. I have here 74 and I have 0.72. The difference is not so large, so I can just replace this with 10 to the 2. Okay, probably if I do, like, again, if I do some really approximate calculations, I can also do this kind of elimination. So 8 is approximately equal to 8.31. So if I want to get some sort of an answer, using only my hands without any calculator. Okay, now what's left over? So I have 10 to the 2 times 10 to the 5, but it's centimeter cubed. Centimeter cubed is 10 to the minus 6 of meter cubed. So this, and this, and what remains is only 10. Meter cubes is eliminated, only 10. So now I get that the answer is something like 355 over 3 times 4, 6, 7. Okay, so, well, we need to get some estimate of that. Let's say, let's divide 3 and 55 over 3, so that would give you 1 and, again, 1, and that gives you probably 8 over 4, 6, 7. And if I multiply this by 4, what would I get? I would get 4, here 4, so I would get 472. That's approximately equal. So this is approximately 1 over 4, so 0.25. Of course, I was making some mistakes, so probably the actual fraction ratio is slightly different, but it should not different but that much. And as a small reminder, if you do the calculations in your written tests, you're allowed to do a mistake probably up to 20 or 30% from the final quantity. So that is actually, if you for some reason have forgotten the calculator, which I don't advise you to do, because if you have the calculator, everything is much simpler than this. But if you have forgotten, you can try to use this kind of tricks in order to get to the final answer. And even if you have calculator, you should estimate the answer, because you can mistype something in your calculator. Instead of, for example, instead of 35.5, you can probably write 335.5, and then the answer would be different by order of magnitude. And that is terribly wrong, because if you have an answer different by order of magnitude, that means that you would have more points subtracted. So sometimes this is even more. Is a better way than using the calculator. So practice both ways. Okay, so now the final, not the final, oh, I'm too optimistic. We have 3 problems left. So this is problem number 2.2 and 12. 2.2 and 12. And you also see, yes, that if I operate with non-SI units, I tend to write the dimensions here. I don't want to be mistaken somewhere on the course. I don't want to make too many conversions, but yes, in order to avoid mistakes, I write the dimensions in the formulas. Okay, so now the problem 2.2 and 12, this is the number. It says that in the vicinity of the triple point, the saturated vapor pressure P of carbon dioxide depends on temperature T. P is a function of T as triple point. Okay, log P equals to A minus B over T. Unexpectedly, where A and B are constants. If P is expressed in atmospheres, then for the sublimation process, okay, well, saturated vapor, sublimation. Okay, for sublimation process, A is 9.05 and B is 1.80 kilokelvins. 1.80 times 10 to the 3 kelvins. 9.5 is P is expressed in atmospheres. Okay. So for the sublimation of this, for the vaporization is the following. For the vaporization is A is 6.78, and B is, well, 1.31 kilokelvin. So that means 10 to the 3 kelvins. Okay, now it looks like completely, well, some kind of a strange stuff, but I know that the pressure is measured in atmospheres. So why do they say that if the pressure is measured in atmospheres, then I have this equation? Because I have logarithm of P, and P is the quantity which has dimension, and you cannot usually take logarithm of the quantity which has the dimensions, because you need to somehow to convert it into dimensionless quantity. And it says that you convert it as follows. You have your pressure, and you express it in atmospheres, then discard the atmosphere, and then use that as the number which you put in your logarithm. Okay, then it becomes perfectly defined. Okay, so what we need to find out? So we need to understand what is this, A minus B over T. We need to probably plot this if you want to get some kind of a better understanding of what happens in this problem. And moreover, we need to calculate A, pressure and temperature at the triple point. This is triple point, at the triple point. And values of specific latent heats of sublimation, vaporization, and melting. So I need to calculate at the second part of the problem. Let's say this would be latent heat of, okay, well, the process is called, how it's called? Sublimation. So for the latent heat of sublimation, we have small s as the latent heat. For the vaporization, V, okay, V is also occupied, nevertheless. And for melting, I need to calculate M. I need to somehow distinguish it from volume, mass, and entropy. So I would have here some specific heat, specific latent heat of sublimation, vaporization, and melting. Because I don't want to have too many variables here, and I'm out of ideas how to name them. Okay, so now, okay, let's try to look at what actually happens in this problem. So the triple point refers to some point on the PET diagram for the phase transition processes. But, well, we know that there is a curve which separates the liquid phase and gas phase. So in here I have, let's say, okay, so if I have it at a constant pressure, so now I have, let's say, liquid, then I turn into gas. So let's say, and here, if I go at lower temperature, I would freeze. So that would give me solid. So these curves can meet at some point. So this point is a triple point, and also there is a curve which separates solid and gas phase without any liquid. So this is where this sublimation process happens. Okay, so here we go. And we know about the dependencies for the sublimation. I have A equal to 9. Okay, well, logarithm P equals to A equal to 9, and then there is something like B. Okay, so that means actually that I have two curves which are described by this equation. Logarithm P is A minus B over T. I have two curves, and these two curves must intersect somewhere, because the first equation describes this curve. Let me label it somehow. So the first equation gives me this curve. This is for sublimation. And the second equation gives me this curve for vaporization. So of course, the triple point would be where these two curves intersect. So first of all, we need to calculate the intersection point. We need to calculate the intersection point. So in the intersection point, the pressure and temperature would satisfy both of these equations. Both of them. So it would give me like logarithm of P triple point should be, okay, so A1, B1, A2, B2, in order to distinguish between them. So it would be A1 minus B1 over T triple equal to A2 minus B2 over T triple. So altogether, well, I can actually solve here the equation for the temperature and obtain the triple point temperature immediately. So I have it like A1 minus B1 over T equals to A2 minus B2 over T. So I need to somehow collect T's on one side and then A's on the other side. So I can write that A1 minus A2 equals to B1 minus B2 times the reciprocal temperature. Okay, so this is not something like higher mathematics, so it's something convenient for you. So now I get the temperature as B1 minus B2 over A1 minus A2. Okay, now I can do the calculations. I'm just curious about what is this triple point temperature. So this is triple, 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 triple here. B1 minus B2. B1 is greater than B2, so I can write that this is 1.8 minus 1.31, all of that times 10 to the 3, and divided by A1 minus A2. Here goes 9.05 minus 6.78. So this is approximately, well, now I can calculate not approximately, 8 minus 3 is 5, but I have also 1 that gives me 0.49 times 10 to the 3. And in here, 9.05 minus 6.78, that should be something like 2.27. Okay, so now if I multiply 0.48 by 10 to the 3, that would give me 490 over 2.27. Okay, let's assume that this is actually 2.3. That's inconvenient to have this 2.27. That's approximately 2.3. So I can divide this by that. Oh, well, I remember my school stuff. 490 over 2.3. So first of all, I have here, I have 1. So it goes like this. That would give me, no. I have 2. So that would give me 46 here. So what remains here is 3. I add this 0, so this would give me again 1. Okay, what's remaining is 7. Okay, 7 is, well, I just can go with 3, and I think this 2 and 13 would be the good answer for this problem. 2.2 and 13 Kelvin. Of course, it's approximate because I have made some approximation here. I have made probably a mistake of 1%. So I have increased the denominator approximately by 1%. So that means that I need to decrease my answer approximately by 1%. So probably it would be somewhere between 210 and 211. So if you want some more accuracy. Okay, so now we have this critical temperature, so now we can also calculate, not the critical, the temperature at the triple point. So after we insert that into the equation, I can get the pressure at the triple point. Pressure at the triple point is, well, now it's going to get really hot because this is 9.05 minus A minus B, which is 1,800, over 210. So that is actually something like 9, but somewhat less than 9, probably 8.5. I would say that this is approximately 8.5. But this is in the exponent, so I think all of our misaccuracies would give a tremendous difference. Nonetheless, 905 minus something like 8.5, or what I get from 8. 8 would give me 1680, so I need 120 more. 120 is somewhat more than 0.5. Probably it's closer to 8.6. Okay, so that's approximately exponent of 905 minus 8.6. So this is actually 0.45. So that probably is. So I need to remember how to calculate the exponent of this 0.45. So that's probably exponent of 0.45 is something like approximately 1 plus 0.45. The second term would be 0.45 squared over 2. And let's look how it corresponds to the first correction. Okay, if I square this, that would give me approximately 1 over 4. So this would give me approximately 1 over 8. Okay, so I would say that this is approximately 1.5 atmosphere. I'm probably terribly wrong here, but somewhere around there. So this is a critical pressure, somewhere around 1.5 atmospheres. .4, so yeah, probably close. So now we are going to get to the second part of this problem. And the second part of this problem is to calculate these specific latent heats of vaporization, sublimation, and whatever else. And as you know, actually, what this refers to? Mostly this refers to that Clapeyron-Clausius equation, which allows it to relate the derivative of pressure over temperature to something else. Okay, so according to the Clapeyron-Clausius equation, okay, here we have parameters, so I think we should leave this here. So let's write also the triple point temperature here somewhere, in case that it is needed, if it's needed. Probably it wouldn't be needed, but I don't know. So let's write. Okay, so now we need to apply the Clapeyron-Clausius equation. The Clapeyron-Clausius equation says that the derivative of pressure over the temperature is something like the change in the specific entropy over the change in the specific volume of corresponding phases. Okay, so that means that this is our latent heat of something, yes, so latent heat, LH, divided by temperature. And since all of these phase transitions involve gas phase in one of the points, that means that mostly I can neglect the specific volume of liquid or solid phase with respect to the specific volume of the gas phase. So I can just divide temperature by the density of the gas. Okay, specific heat by the density of the gas. So now I need to calculate density of the gas. This procedure I have done multiple times during the seminars, calculating the density of the ideal gas. So I assume that my gas is ideal. We are far from the critical point. The gas is very rarefied, so I can write that PV equals to m over mu times capital RT. So that's equation of state. So if I take m to be equal to 1 kilogram, that means that volume is equal to the specific volume, or to the reciprocal density. And that means that P times rho equals to RT over mu. So from here I get my, 1 over rho. So 1 over the density is RT over mu P. In here I have 1 over density, so I don't even need to calculate exactly the density. I just can plug it exactly into this denominator. So I would have LH over T times RT squared over mu P. Good. So RT. So that would give me mu P over RT squared times latent heat. LH. So I can, based on this expression, I can calculate actually all of the quantities which I need in my problem. So let's put this dependence into my equation. So in here, a logarithm of pressure is some kind of this equation. So that means that logarithm of pressure is, so if I take the derivative of logarithm of pressure of the temperature, d log p over dt, that is actually the dp over dt divided by pressure. Okay, that's actually exactly what I have. If I take this pressure and get it to the left-hand side here, then I would get actually the derivative of the logarithm of pressure of the temperature. So now I would get the following, that this is minus, okay, plus b over t squared is equal to mu times latent heat over RT squared. Okay, t squared is eliminated from here, so that is how it should be. So temperature is really not needed. So then I can get the latent heat as R times B over mu. R times B over mu. Okay, so what liquid we are studying actually in this problem? Carbon dioxide. So this is carbon dioxide, CO2. Carbon dioxide has molar mass of, okay, for molar mass of carbon, $12. Well, when I studied in school, we actually used molar mass of carbon, or actually as the, I think, as the definition of 1 mole. So probably like 1 mole is something which makes like 12 grams of carbon. 16, yes, oxygen has 16, but we have 2 atoms of oxygen, so that would give us 2 times 16, that is 32. 32 plus 12 would give you 44. 44 grams per mole. Good. So now I can place it in here. So latent heat is 831 joule per mole Kelvin. I don't want to get from grams to kilograms, so I divided by 44 grams per mole, and I have mole eliminated. B is measured in kelvins, so Kelvin is also getting eliminated. So I have latent heat in joules per gram. So, well, pretty much nice answer, but well, multiplied by B in kelvins. So in this way, I would get only 2 of the 3 quantities. I would get the sublimation latent heat and latent heat of vaporization. Now the final question: how to calculate melting heat, specific heat of melting? So probably there should be some relation between this, and that in the triple point. So okay, let's think about it. So let's say we are in the triple point. In the triple point, okay, it goes like this, not like this. And probably for most solids which are not for most solids which are not ice, then actually this part also looks like this. So it goes to the right, not to the left. Okay, so we are in the triple point. So it means that we can actually do a transition melting. How we can do melting? We can do this in two steps. Melting is going from solid phase to the liquid phase. So we can do this in two steps. So in here I have solid, liquid, and gas. To get from here to here, I can do first I can go to the gas phase, and then I can get to the liquid phase. So in the first process, I would need to spend the amount of heat of sublimation as latent heat of sublimation is S, and specific latent heat of sublimation in order to convert 1 gram of solid into 1 gram of gas. But if I convert 1 gram of gas into 1 gram of liquid, I don't need to spend any heat. I actually get something in return. Because if I want to vaporize liquid, I need to spend heat. But if I go in the backward way, that means that I have some heat in return. So I need to subtract the amount of heat, the specific latent heat of vaporization. Okay, so that would give me specific heat of melting. So indeed, these three parameters are, well, they are related by this way. Well, actually, I can express this relation more mathematically. Specific heat of some process means that, okay, let's say, specific heat of the phase transition is actually equal to the difference in enthalpy of 1 mole of 1 kilogram or 1 unit of mass of one phase minus 1 unit of mass of the second phase. Because these processes of vaporization, melting, and sublimation, they happen at the constant pressure. That's why for all the processes which happen under constant pressure, the amount of heat which you supply to the system equals to the difference in enthalpy. So, okay, so I have this specific heat, I have this specific heat, and I need to calculate lambda 23, which is H2 minus H3. So indeed, I can do this in this way, that I can just calculate H1 minus H3 minus H1 minus H2. So indeed, this is lambda 1,3 minus lambda 1,2. Once again, the same expression. Okay, so if you don't have any questions regarding this problem, we can move to the next one. I'm not going to obtain the numerical values here, because I think we don't have too much time for this. Yeah, so we have 2 problems left and half an hour of our class. Any questions? No questions, okay. The next problem is 2.201. Now we do problem with Wonderwise gas. It says that we know Wonderwise constants, so we know A and B. Wonderwise constant, not A and B from the previous problem, but different A and B's. We need to calculate maximum volume which water of mass kilogram can occupy in a liquid state. I like this formulation, so let's look at this once again. Maximum volume occupied by 1 kilogram of water in the liquid phase. Kind of a sophisticated formulation here, very sophisticated. So maximum volume occupied by 1 kilogram of water in the liquid phase. So it is actually a cryptic message, and this cryptic message is for what? So let's look in isotherms of water. And here, and here. And as we see, as we increase temperature, the volume of occupied by liquid phase, so this point corresponds to 100% of liquid. 100% of liquid. So as you see, as I increase temperature, the volume occupied by liquid increases. So indeed, the liquid obeys the, how it's called, thermal expansion law. So if you increase the temperature, the volume occupied by liquid also increases. So I think it should not make you wonder that volume of liquid increases. But this process cannot continue indefinitely, because there is a maximal temperature when the liquid can actually exist. And the maximal temperature is called critical temperature. And in this case, the maximum volume which is occupied by liquid is called critical volume. So actually, the first question to the problem is a cryptic message that actually means to calculate critical volume of liquid, but the specific critical volume. So in the case of A and B parameters, we get critical volume of 3B, and this is for 1 mole. For 1 mole of water. So, but for 1 kilogram, we need to calculate the number of moles in 1 kilogram. So in this way, this Vmax is actually nu times V critical, where nu is m over mu times V critical, and where m is 1 kilogram, and mu is, I think this is 18 grams per mole, and times 3B. Okay, so that gives you 1,000 over 6 times B. Well, assuming that we know that, we can determine that. Probably these A and B quantities can be found in at the end of the Irodov book. Okay, now the second question. B, calculate the maximal pressure of the saturated water vapor. It's indeed, once again, we have a cryptic message. Maximum saturated vapor pressure. So previously we had something to do with the maximum volume, but in here we have maximum saturated vapor pressure. So once again, we look at the dependence of the saturated vapor pressure as a function of temperature, and we see that it increases all the way until the critical point. So once again, we need to calculate the critical pressure. And again, we have a formula for that. And the critical pressure is A over 27B squared. So both of the questions of the problem are actually very simple in terms of calculation, but they are cryptic in terms of formulation. You need to understand what the authors of the problem want from you. And in these both ways, they actually mean for you to calculate the critical parameters of water. Okay, now we go to the next problem. Any questions about this? No. The next problem, 2.60. This is indeed the last one, so I think after that you can go home. 2.60. Two thermally insulated vessels are interconnected by a tube equipped with a valve. Well, once again, I think the usual formulation. Nothing strange here. One vessel of volume V1 of 10 liters, V1 equals 10 liters. Okay, liter is what? I mean volume, but in terms of SI units. How many cubic meters is that? 1,000? 1,000 centimeters cubed, or probably 1/1,000th of meter cubed. So 10 to the minus 3 of meter cubed. Okay. So we have 10 liters, which contains 2.5 moles of carbon dioxide. Once again, carbon dioxide. And the other vessel of volume V2 equal to 100 liters is evacuated. It contains nothing except for vacuum. The valve having been opened, the gas adiabatically expanded. Well, that's not adiabatic expansion, but that's free expansion. Assuming the gas to obey Wonderwise equation, find its temperature change accompanying the expansion. So we consider here free expansion of gas. Free expansion is one of two most important irreversible processes which we just discussed in the thermodynamics course. One of them is Joule Thompson process, which we have discussed half an hour ago, probably, or an hour ago. And this is free expansion. In the free expansion, internal energy of the gas doesn't change. And the reason for that is that there is no heat exchange in between the gas and environment. And secondly, there is no work being done either by the gas or on the gas. So therefore, the internal energy should remain the same. But, well, we need to calculate the temperature change. Any guess about this? No change in internal energy. What is the change of the temperature? Huh? Okay, if it were ideal gas, what would be the answer? Zero. So internal energy is only the function of temperature. So as you increase the volume, then you need to keep the temperature constant. But we deal here with Wonderwise gas, and in the case of Wonderwise gas, internal energy is the function of volume. So internal energy of Wonderwise gas, we need to remember that this is equal to CVT minus A over V. That's for 1 mole of gas. That's for 1 mole. For 1 mole of gas. The derivation of this equation is in the lecture. So you can check the derivation. If you don't remember where this equation comes from, you need to check out the derivation there. Okay, that's the internal energy for 1 mole of the gas. But we don't have 1 mole of the gas. We have 2.5 moles of the gas. So how we calculate the internal energy for 2.5 moles of the gas?
Only the extensive variables.
Yeah, so we need to look which variables in here are intensive and extensive. So U is extensive variable. So I need to multiply. So if I want to calculate U of new moles of the gas, I need to multiply this by internal energy per 1 mole of the gas. But in here, volume is also extensive variable. So if I go from new moles to 1 mole, that means that my volume should be decreased by a factor of nu, as all the extensive variable. But T is intensive variable, so in this, there is no change of T. So I need to insert all of this into this equation and get the final answer. So that would give me nu times CVT minus A over V over nu. Okay, so this is nu CVT minus A nu squared over V. That's the internal energy of new moles of gas, and we change the volume. So that means that I can write that nu CVT1 minus A nu squared over V1. This is the initial internal energy. I need to equate this to the final internal energy, nu CVT2 minus A nu squared over, okay, final volume would be, if I open this valve, and in here I also have V2, the final volume would be, yeah, so it would be V2 plus V1. So like your hand memory wants you to write V2 here, because you have here T1, V1, T2, V2, but that's wrong, because final volume is V1 plus V2. Okay, so from this I can determine the temperature change. So I need this to get to the right-hand side and this to go to the left-hand side. So that gives me A nu squared over V1 plus V2 minus A nu squared over V1. That would give me nu CV T2 minus T1. So from this I get that delta T is equal to minus, okay, let's take A nu squared over CV, over nu CV actually, nu CV. So nu is left here. And here goes 1 over V1 minus 1 over V1 plus V2. So that would be V2 times over V1 plus V2. Okay, now I write it again here to fix the final answer. Delta T is minus A nu over CV V2 over V1 times V1 plus V2. So here goes 10, here goes 110, here goes 100. Okay, that can be calculated. That can be calculated if we know Wonderwise parameters for the carbon dioxide. Again, these parameters of carbon dioxide can be found by the end of the book. Okay, we have 10 minutes left, so we can get this to the final answer actually. Okay, I'm going to write that this is, okay, V2 is 100 liters, V1 is 10 liters. Okay, we need A and we need CV. For the molar heat capacity at constant volume of the carbon dioxide, we need to remember that carbon dioxide is, the molecule of carbon dioxide contains 3 atoms, and for 3 atomic gas, the CV should be equal to 3R. And for A Now let's look. Oh. For carbon dioxide, Wonderwise constant is 3.62 of atmospheres times liter squared over mole squared. 32 atmospheres times liter squared over mole squared. Okay, so we have volumes in liters, we have the amount of matter in moles, so everything is ready for calculation. Okay, so delta T equals to 3.62 atmospheres liter squared over mole squared multiplied by amount of gas, which is 2.5 moles, divided by CV, which is 3R, which is 3 times 831 times Joule over Kelvin over mole, multiplied by V2, which is 100 over liters over 10 liters times 110 liters. Okay. So after I eliminate this and this, I am left only with 11 in the denominator. So in here I have 3.62 atmospheres times liter. Okay, moles are eliminated, and everything is divided also by joule. Atmospheres times liter over joule. So 3.62 times 2.5 over 3 times 11 times 831. Okay, how it can be done? Well, I think that the 3.62 times 2.5 is approximately equal to 9. The reason is the following, that 2.5 is 1/4 of 10. So I need to divide this by 4. So if I divide 36 by 4, that would give me 9.05. So that would give me 9.05 atmospheres times liter over joule. And here goes 3 times 11 times 831. Okay, well, I think that this 9 and this 8.3 are approximately the same values. So, but there is a slight difference only between them. Let's see how much this difference is. So this is approximately 0.7 of difference, so this is 10%. So this is by 10% larger than this. And here we have 11, and 11 is by 10% larger than 10. So if I eliminate this and this, I can replace 11 by 10. So that would give me 1/30 atmospheres times liter over joule. Now I need to do this unit conversion, which is, I think, by far the hardest part of this calculation. So atmosphere is 10 to the power of 5. Liter is 10 to the minus 3. So that will give me Pascal, meter cubed. And as we know, Pascal times meter cubed is joule. So this will give you 100. So this is 10, 100 over 30. So this is approximately 3.3 of what? Of kelvins. And I hope the answer is close to the correct answer. Let me check. This is 2.60. I wanted to find the answer, but the program in which I opened the Irodov book just hanged. 2.60. Probably the computer doesn't want to disappoint me. Okay. No. Well, it says minus 3 kelvins. Okay, I got the sign wrong.
In the formula we had minus here.
Yeah, we had minus here, and I have forgotten that minus. So I was doing all of those calculations, but I was still wrong by 10%. Well, unfortunately. Okay, thank you for attention. I think we are now finished. If you have any questions and whatever, then you can ask them.